So far we have looked at how pointers can be thought of as just some kind of a value that literally holds the address of a variable or some content in memory. And what that means is that a pointer basically is an address, in other words it is a number, which means that in principle you could also perform arithmetic on pointers. You could add values to pointers, you could potentially subtract values. It probably does not make much sense to multiply pointers together, but at the end of the day they are just integers. So what kind of arithmetic with pointers actually makes sense, and what are the things that we could do, and how do we potentially put that to use is something that we will now look at. So the main thing that we are trying to understand over here is an address is an index of a location in memory. In terms of an array, it is basically some kind of an offset from some starting point. In other words, an array is basically declared as a starting point, and every successive location in that array is an offset into that offset starting from that location. And in other words, with just a simple calculation based on the starting point and the offset, it is possible for us to identify any location inside the array. So we typically think of array addressing, in other words, as a base and offset combination. The base is typically the address of the first location in the array or the list, and the offset is how many address locations do we need to move forward from here in order to get to whichever location we are interested in. And because of the nature of arrays, the fact that they are homogeneous, each of the data types present inside the array is of a fixed size, it is possible to perform this computation or this indexing in a very compact and efficient manner. So another way of looking at this in terms of the syntax afforded by the C language is that we usually use the syntax A of I, right? This is usually pronounced as A of I. And what we mean over here, and the notation that we use is square brackets rather than the typical round brackets that we use when we are talking about functions. So the square brackets indicate array notation, right? So A of I indicates the ith element of the array labeled A. And what we say is that this notation A of I is exactly identical or means exactly the same thing as this particular notation, which is star of A plus I. We usually pronounce this as star of A plus I. And what we mean over here is we take the starting point A, we need to know what kind of pointer it is. Is it a pointer to a character, is it a pointer to a string, and so on. And when we add I, we are moving I locations of that data type forward in memory, and then we look at the content present at that location. So what exactly do I mean by this I locations forward? That's something that we will need to look at and understand in a little bit more detail. Okay. Now a couple of things to keep in mind over here. A is a name, right? After all, it's a variable, which means that it's a name given to an address location, right? Just like any other variable in C, the name of a variable basically is some kind of an alias or some way of some kind of a shortcut to refer to a particular location in memory. In the case of C, it is the pointer or the address of the 0th location in the array. Okay. What I mean by that is that normally when we are talking in plain English, we talk about the first element of an array, whereas in C we would normally talk of A of 0 being the first element. Just to keep things simple, we usually talk about it as the 0th element of the array, right. So when we say the 0th element of an array, what we actually mean is the first element that is present in the array. This can get a little bit confusing if you are not used to it, but usually it sort of resolves itself because the meaning is mostly obvious in context. When in doubt, it is always better to say A of I and make explicit what I is. The important thing is, if we have an array with 10 elements, the very first element that we can refer to is A of 0, and the very last element in that array is A of 9, right. So A of 0, A of 1, A of 2, and so on up to A of 9 are the 10 elements that are present in the array. We usually use this, the term that is used to refer to this is called zero based addressing. C is one of the languages that uses zero based addressing. So is Python. So it is most probably familiar to most of you if you have done any kinds of programming, because Python is probably one of the more common languages. However, there are other languages that use 1 based addressing, where a of 1 would be the first element in an array. Good examples of this, one of them is MATLAB, right, which is a very common language used especially in the context of signal processing and a lot of numerical calculations. And another one is Julia, which is also a very interesting language in terms of scientific computing and has some very nice features in terms of how it can give you very high performance code, and it tends to use a similar kind of 1 based addressing. But as far as C is concerned, it is very clear, it uses 0 based addressing, and I over here refers to the offset in terms of the number of elements, not the number of bytes. Okay. And this is an important thing to keep in mind. This means that the size of an individual element must be known, and of course it is known to the compiler. So you need to understand that the star of a plus I is not something that is interpreted at runtime. It is the compiler that looks at this piece of code, it sees what type of data A corresponds to, and it sees the size of that, and when you need to increment by I elements, it basically advances by I locations of the data type of A. What that means is, if something is declared as an int star, then when I increment that location p plus plus, what happens is I increment by 4 bytes, because 4 bytes is the size of one integer in C. Okay. On the other hand, if something is declared as a char star p and I do p plus plus, then the compiler knows that p actually refers to characters, and when you do p plus plus, you need to increment by 1 byte. So the increment happens and the address location that you get goes up by 1. So in other words, the p plus plus or any kind of arithmetic that you do, p plus I or a plus I, depends on the data type of A or P, whatever the pointer is that you are actually referring to over here. It does not depend on I, right? I over here could have been declared as an int, it could have been declared as short, it does not matter, any number, or it could have been a constant number. What it is telling you is that you want to take the address corresponding to the starting point of A plus I elements of the same data type as what A points to. Now, what exactly do we use for representing I does not really matter, it is just a number as far as we are concerned. Now, interestingly, of course, what this normally means is that the A of I is used to refer to the ith element in A. You can go forward from A. What that also means is I could have done a minus as well, A minus I, and it would have performed the computation of going backwards, and if you think about it, most likely that is going to end up in some area of memory that is not part of what you were supposed to access, right. Now, what happens in the case of addressing in C is that a pointer at the end of the day is just a number, it is a location somewhere in memory. It is possible for me to take one pointer and interpret it as another pointer. An example for that would be, let us say that I declare a variable int a of 10. What this notation means is, A is an array consisting of 10 elements, which means that A itself is actually a pointer. What does it point to? It points to 10 elements of type integer. In particular, the variable A by itself points to the 0th location of that array. Okay. So what would happen, in other words, is this A over here has exactly the same meaning as the address of A of 0, which is denoted by this ampersand A of 0 that we have that I have written over here, right. So it is the address of the first element in A. Now that would be some location in memory, right. We do not exactly care where in memory it is, but it would be something out here, and what we can see is that A of 0 would be some 4 bytes. The A of 0 by itself would actually refer to the byte corresponding to, whatever A of 0 or whatever it is, and then the plus 1, plus 2, plus 3 would be the 3 other bytes that you have present as part of that integer. Now I could also go ahead and declare another pointer short star b. Now short is a data type of 2 bytes size, right. And what I have done over here is I have basically said, take short star b and take the variable A, which is after all a pointer, but from now onwards treat A as a pointer to short, right, and assign that value to B. So what this means, in other words, is B is now potentially can be thought of as an array, right. And what I would have in this case would be that B of 0 would contain some memory, if I accessed B of 0, the compiler would go look up some location in memory corresponding to where B points to, take 2 bytes from there, interpret them as a short value and give me the results. B of 1 would increment this B location by 2 bytes and go to the next location and pick up 2 more bytes over there. If you think about it, this B of 0 and B of 1 both together lie within the 4 bytes that correspond to A of 0. So this sort of gives us some interesting ideas. Basically what it's telling us is, I have a 4 byte integer. If I wanted to split it up into 2 short values of 2 bytes each, I could basically just go ahead and declare a short pointer to the same memory and now start reading it out as short values, and I would get them 2 bytes at a time. I could do the opposite, which is that I could basically fill in locations in memory using a char pointer and then read them out 4 bytes at a time and treat them as integers, right. So many different combinations are possible over here. The bottom line and the most important thing, the only thing that you really need to know in order to understand all of this is, a pointer is just pointing to some location in memory, and any addressing or any access that you do with respect to that pointer is entirely dependent on what data type that particular pointer name has been defined to be. In other words, if I access using B, the compiler knows I am trying to access short values. If I access using A, it knows that I am going with int values, right. And the compiler then takes care of pulling out the appropriate number of bytes, packing them together into int or short or whatever other data type you want, and giving you the correct result, right. So always keep that in mind. The only real way of understanding what pointers are doing is to just treat them blankly as something that's pointing to a location in memory, and anything further about what is actually being pointed to, you need to know which data type that pointer was declared as. That's all. Now, a related question when we talk about declaring an array is that you can think in terms of something called an array bound, right. So what are bounds in an array? If I have declared an array as int a of 10, what I mean logically is that a is a pointer to an array, right, and that array should contain 10 elements. I could say that it's up to 10 elements because maybe I don't want to use all 10 of them. I might also declare an array of a certain size and not use all the values that are required in it. There can be a number of scenarios where that happens. For example, I might declare a string array, which we'll get to later, of a certain size, just so that it's long enough to accept whatever name I might want to enter. But I might not actually have a name that's that long, right, in which case some of the bytes that have been set apart for that string are not being used. That's perfectly fine. Similarly, you might have a scenario where maybe you want to ask the user to enter a series of numbers and then perform some computations with them, but you don't know in advance exactly how many values the user is going to enter, right. So you make a guess, you put an upper bound and you say maybe at most 100, and you declare an array of size 100 elements, allow the user to enter anything from 1 to 10 to 25 up to 100 elements, but not more than 100. So that would be a reason why you would declare an array to be of a fixed size, right. But now comes the question, what actually happens if I try accessing a of 11, right? And the short answer is the compiler will try to access a of 11, right, because after all, what is a of 11? It is, you take the starting location of a, add 11 to it and take the pointer, right. And this could be of whatever data type you have. In the case of int, it would basically add 11 into 4, so 44 bytes to the address location starting with a, and then try to access the next 4 bytes and give you the result that's present over there, right. Now, is that outside the array? Yes, it is, but is that outside the memory of the computer? We don't know, right. Is that outside the memory that's allocated for this particular program? We do not know. The bottom line is that C, the language or the compiler, does not actually enforce these kind of bounds. It does not check whether you are accessing something inside or outside what you are permitted to, or whether an array is being used in order to access something that is actually permitted, that is part of what it was declared to contain, right. Now, there are some very specific scenarios in which that can actually even be useful, but in most cases this is bad news, right, and it leads to a number of the bigger problems with C. In particular, as soon as you have written more than anything trivial in terms of C programs, right, especially the moment you have touched pointers or arrays, at some point you are going to see these kind of messages: segmentation fault, segmentation violation, bus error, right. There are a few different terms that are used to indicate this. All of them will most likely also be accompanied by a crashing program, basically meaning that the program just comes to a halt, right, does not give you the exact result that you wanted, and clearly something has gone wrong, right. Now, that is actually speaking probably one of the better scenarios. There is also an even worse scenario where it does not complain, it actually allows you to access some data, but it is data that you were actually not supposed to have access to, right. And why I call this a worse scenario is there can be bugs of this sort where potentially one program reads the data corresponding to another program. In the worst case scenario, it could be something like somebody writes a program on one computer, on a computer where other people are also running programs, and is able to read information including, let us say, the password or other personal information corresponding to the other user, right. Now, in most cases that does not happen. It is much more likely that you would get a segmentation violation and the program would just crash. That is bad enough, because you do not want a program to be crashing, right. You want it to be able to prevent certain kinds of memory accesses that go out of bounds, right. Ideally, if the compiler itself would prevent you from writing code like this, a of 11, a of 10, a of 25, because clearly it knows that they are outside the bounds of this array, that would probably be a good first step. In case for whatever reason that is not possible, then at least ideally you would not want it to crash completely. You might want it to raise some kind of an error signal that could maybe be caught, and you say, okay, something went wrong, but we can recover from it and proceed. But this business of array bounds is one of the bigger problems potentially that you will encounter when writing C code, right. The simplest way to sort of avoid something of this sort is try and keep your pointer arithmetic and such things to the minimum, and be very systematic about where and how you declare variables and how you use them, right. That is easier said than done. There are other languages that actually enforce this in a much more systematic manner and prevent you from making these kind of mistakes, and in a lot of scenarios it is actually preferable to use those kind of languages, right. C does not, like I said earlier, right. C is one of those languages which is very close to the hardware, the actual computer that you are running on. It allows you to do a lot of things that are potentially dangerous and that can cause problems. Understanding what those are is good, and it is very useful for you as a programmer, even if eventually you decide that it is not worth taking the risk of writing programs like this in C, and you would rather use a safer language in other contexts. Now, one word regarding how the memory gets allocated, right. Typically, if I declare two variables, int a of 10 and int b of 10, in a lot of scenarios what would actually end up happening over here is that they would be allocated one after the other in the memory of the system, right. So, you would have this block of memory, you would have one chunk of data corresponding to A, and you would have another chunk of data corresponding to B. Now, whether A goes to the higher memory addresses, B goes to the lower, or the other way around, that depends partly on whether the compiler, whether the machine is big endian, little endian, and a few other aspects of the compiler. In most cases you are not supposed to know, right, which is why I am saying that there are no guarantees. You cannot in general be sure of which is going to occur before which. But if it happens this way, let us say that for whatever reason A of 0 corresponded to this memory location and B of 0 corresponded to this memory location, The interesting thing is that potentially now what I have is that A of 10 actually corresponds to B of 0, right, because after all this would be star of A plus 10, which would basically correspond to this particular memory location, right. This is not something that is guaranteed. It depends on multiple factors including the Indianness of the computer, which definitely means that code which is written in C, it may work on an x86 processor, it probably will not work then on an ARM processor, right, or a Sun Spark processor and so on. So this is not something that is to be relied upon or to be used in a systematic manner, but there is a possibility that you might actually end up with bugs that behave strangely that actually come down to this, the fact that you are trying to access something out of bounds, but just by luck you end up accessing something from another array. The worst scenario here is that because of this there are no segmentation violations, because after all you are not trying to access memory which is out of bounds for you, but the program sometimes behaves correctly, sometimes does not. It entirely depends on what is present in B and what is present in A and what was expected to be present in the different values of A.